Welcome to today's talk on FinFETs, the backbone of modern transistors. The talk outline today will start with the early history of the IC industry. Then I'll move over and talk about Moore's Law. Then discuss planar transistors versus FinFETs. Then I'll go into more detail on the FinFET structure and their fabrication. And I'll finish the talk by going over what's next after FinFETs. And this is just a note to myself, don't forget to shamelessly plug my YouTube channel. And my YouTube channel is called Chipcraft. And if you like any of these presentations, please like and subscribe. Thank you. Way back in December of 1947, the first functional point contact transistor was built and tested at Bell Labs by John Bardeen, William Shockley, and Walter Brattain. And those three went on to win the Nobel Prize for Physics in 1956. If you look at the right side of the drawing here, here's a picture of the first point contact transistor. Now, I'm not sure if this is an actual photo from 1947 or a replica, but this is what it looked like. A bunch of germanium crystals pushed into each other with a bunch of wires hanging off them. Now, this was just a single transistor. However, the concept of an integrated circuit where multiple transistors or devices are incorporated on the same substrate didn't really take off until the late 1950s, about a decade later. In 1958, Jack Kilby at Texas Instruments created the world's first integrated circuit. Now, Kilby's invention was what we would call a hybrid today. He incorporated a mesa transistor and a capacitor and several resistors on a common germanium substrate and connected them using bond wires to create an oscillator. Now today this may seem trivial, however at the time this was groundbreaking. Kilby was looking for ways to miniaturize existing circuitry. There's also a picture of Kilby's original invention off to the right here. Now in his long career with Texas Instruments, Jack Kilby went on to create many inventions and innovations that helped to push the industry forward. In '61, Kilby built the first computer using integrated circuits. In 1967, he and two of his co-workers invented the first pocket calculator to show how useful integrated circuits could be in daily life. Kilby held more than 60 patents. In 1982, he was elected to the National Inventors Hall of Fame. Jack Kilby received the National Medal of Science in 1970, the National Medal of Technology in 1990, and the Nobel Prize for Physics in 2000. He was truly one of the industry's early visionaries. And there's a picture of Jack Kilby off to the right here. Now, Kilby's work in 1958 on germanium hybrids got the integrated circuit ball rolling. However, the industry didn't really take off till a few months later in 1959 when Robert Noyce and others at Fairchild Semiconductor developed the monolithic silicon IC. A monolithic IC is an electronic circuit manufactured on a single piece of silicon. It integrates all the essential components like transistors, resistors, capacitors, and their interconnect onto a single structure. This is something that today we would recognize as a modern IC. Off to the right here, we have a picture showing a lot of the Fairchild Semiconductor co-founders. I wanted to mention a few of the more well-known people in this picture. In 1957, Gene Horney proposed the planar process to replace the mesa transistors of the time. By 1960, the planar process or derivatives thereof had become the dominant process used to build semiconductors for the next 50 years. So we're talking 5 decades here, so that's quite an accomplishment by Gene. In 1959, Robert Noyce proposed a way of interconnecting planar devices on a common substrate by depositing and etching metal, and the monolithic IC was born. And today, we use very similar processes where we deposit and etch metal to create on-chip interconnects. So that invention is still being used in some form today. In 1968, Gordon Moore and Robert Noyce went on to found Intel Corporation, Gordon Moore may be best known for proposing Moore's Law, and I'll talk more about that later in this presentation. I did want to show you one example of an early product from Fairchild Semiconductor. In 1961, Fairchild Semiconductor introduced the MicroLogic Type F flip-flop. This was the first production planar IC, and it was designed using resistor transistor logic, that's RTL, and had a whole 4 bipolar transistors and several resistors on board. Now BJTs, which stands for bipolar junction transistors, were commonly used in the early days because MOS transistor fabrication techniques had not yet been perfected. So this die was etched to fit into a small round can package. And if you look on the left side of the drawing here, here's the schematic of what that flip-flop looked like with its 4 bipolar transistors. In the middle here, you have a functional diagram and how it pinned out in the can package. And then at the far right, you can see an actual photograph of one of these die that's been etched into a round shape. And today, anyone who's familiar with integrated circuits could look at this and say, yes, this looks a lot like a modern integrated circuit. You know, there's transistors and resistors on board with interconnect above. In 1965, Gordon Moore, co-founder of Fairchild Semiconductor and Intel, predicted that the number of transistors on integrated circuits would double every year for the next decade. This prediction was later revised to doubling every 2 years. Now, Moore's empirical evidence did not directly imply that this historical trend would continue forever. Nevertheless, his prediction has held fairly well since 1975 and has since become known as Moore's Law. And let's take a look at this chart over here. On the x-axis we have the year, and on the y-axis we have the transistor count on microprocessors. And the red dashed line here indicates what Moore's Law would have predicted. And it's not an exact linear relationship here, but it follows the line pretty well. Moore's prediction has often been used in the semiconductor industry to guide long-term planning and set targets for research and development. Perhaps it's a self-fulfilling prophecy, but again, this is very impressive. Over many decades, Moore's Law has been followed by the industry. Over those same decades, the failure of Moore's Law has been predicted many times. For 40 years, the IC industry concentrated on improving traditional planar transistors, and many significant and ingenious advances were made in order to maintain the exponential growth Moore predicted here. However, in the early 2000s, traditional planar transistors, they started to run out of steam, and it sure looked like Moore's Law was finally going to peter out. Enter the FinFET. Intel introduced FinFET technology to production in 2011, and since then, FinFET production has grown drastically, spreading to all the major foundries. A FinFET is a type of MOSFET with a 3D non-planar structure where the gate is wrapped around 3 sides of a thin vertical fin or channel, improving control and reducing leakage current compared to a planar FET. And you can see a FinFET off to the side here. The gate oxide is wrapped around the channel, and we'll talk more about that later. So let's compare a traditional planar FET to a FinFET. And I've attempted to use similar color coding in both these drawings below. On the left, we have a traditional planar NFET. And if we apply a positive voltage to the gate terminal, the electric field creates a conducting channel between the drain and the source. And I think many of you are probably familiar with this. This technology has been around for 5 decades or so. On the right, we have the basic FinFET structure, and it operates in a very similar manner to a traditional planar FET. It has all the same terminals, drain, gate, and source. And if you apply a voltage to the gate terminal, it creates a conducting channel from the drain to the source, just like the planar FET does. However, the difference is the drain, the source, and the conducting channel are all now formed as part of a vertical fin that juts out of the substrate. And you can kind of see the fin in the picture here. This new structure allows the gate to wrap around all three sides of the channel, not just one, as you can see over in the planar MOSFET. So this structure is sometimes called a tri-gate because there's really a left gate, a right gate, and a top gate surrounding the channel. The conducting channel has a width, a length, just like a planar device. However, now it also has a third dimension, the height. And it turns out that this structure has some significant performance advantages over the planar structure. Lifting the channel above the substrate reduces all the parasitic capacitances that are competing for control of the channel with the gate capacitance. And wrapping the gate around the channel on three sides increases the gate to channel capacitance, increasing the gate control. This improves the electrostatic control of the channel and reduces short channel effects like drain-induced barrier lowering, also called dibble. This leads to a steeper sub-threshold slope, meaning a smaller voltage change is needed to turn the transistor off, and thus significantly reducing leakage current. When you have 100 billion transistors on a chip, the power dissipation due to leakage current becomes an important consideration. And I believe the latest Apple chip has 184 billion transistors on the chip. So 100 billion transistors is not unheard of. Due to the method of fabrication, all the fins are the exact same size. And I'll talk more about this later. This means if you want a transistor with more drive capability, you place multiple fins in parallel. This is what's known as fin quantization. Each transistor is constructed from a whole number of fins, such as 1, 2, 3, etc. And the drawings below here just show two different ways of depicting this. The transistor on the left has three fins, all connected in parallel from one source terminal to one drain terminal. And the transistor on the right, it's just a different way of drawing it, also has three fins. So once again, that's called fin quantization. Prior to the introduction of FinFETs, the industry had already developed strained crystal techniques to improve carrier mobility and increase the drive current of planar devices. Similar techniques are now being used with FinFETs. Compressive strain is introduced into the PMOS channel to increase the hole mobility, and tensile strain is introduced into the NMOS channel to increase electron mobility. And let's look at these two drawings down below. Here we have a FinFET, and we're calling this a PMOS FET. So what we want to do is we want to create some stress on the channel to push the channel inward, creating a compressive strain in this channel area to increase the hole mobility. And in a similar manner, if we have an NMOS on the right here, what we want to do is we want to create a tensile stress on the channel by pulling on the fin away from the channel area. Now, how is this done? So to show how this compressive or tensile stress is created, special stressors are epitaxically deposited over the source and drain regions of each fin. And that's what these red areas are in this drawing below here. Now these stressors are typically made out of either silicon germanium for the PMOS device or silicon carbide for the NMOS device. Now germanium atoms are slightly larger than silicon atoms, and carbon atoms are slightly smaller. The lattice mismatch between the stressor material and pure silicon causes either the compressive or the tensile stress that you're trying to achieve. And once again, let's look at this drawing over here. So in this case, the fin is kind of hard to see. It's underneath the stressor material here. And you're applying a stressor to the left and right side of the fin here. And it's either, again, silicon germanium or silicon carbide, depending on whether you want to create compressive stress or tensile stress. So both methods work. However, these techniques work much better at improving the mobility of holes than they do for improving electron mobility. And the results are almost a 1-to-1 ratio of electron to hole mobility in FinFETs versus the standard 3-to-1 ratio in normal unstrained silicon. Because of this, the NMOS and PMOS devices used in FinFET logic gates, such as inverters, will be made the same size instead of the PMOS device being roughly 3x the size in a normal unstrained silicon process. And here we show this in a pictorial form here. Here we show a typical inverter with transistor sizing in an unstrained silicon process. And typically the PMOS device, the W over L ratio, would be about 3x that of the NMOS device. And again, that's to make up for the 3-to-1 difference in mobility of holes versus electrons. However, over in FinFET device, typically what we're talking about is the number of fins used in the PMOS device and the number of fins used in the NMOS device for an inverter would be identical, because due to this strain engineering, the mobility of holes is almost identical to the mobility of electrons. So the fins in the channel area are fully depleted intrinsic, that means undoped, high resistive silicon. This means there's no added doping in the channel like there is in most planar devices to adjust and set the threshold voltage. The threshold voltage of FinFETs is set by other means that I'll discuss later in the talk here. So the advantages of the fully depleted channel are it improves gate control and gives you better off isolation, and it lowers power consumption. Now, just as an aside, there's also a type of planar device that uses a fully depleted channel, and it's done for very similar reasons. And it's called an FDSOI device. That stands for fully depleted silicon on insulator. And I show that device over here. So again, it's a fully depleted channel, and it has a buried oxide underneath to mark the channel between the gate on top and the buried oxide on bottom. Now this planar fully depleted SOI FET can also bias the region under the buried oxide by using an additional contact. And this is known as a bottom gate or a back gate. And this terminal can be used to adjust the threshold voltages and the linearity of the fully depleted SOI FET. So both FDSOI and FinFETs offer significant performance improvements versus traditional planar FETs. Typically, FinFETs are faster and have lower leakage current, making them the go-to device for high performance applications. However, FDSOI FETs cost less due to their simpler manufacturing processes. So there are two basic ways to isolate FinFETs from one another. You can have a bulk FinFET, as shown in the left drawing here. This type of FinFET needs to be junction isolated using N and P wells similar to standard bulk CMOS, and I show more about this on the next page. Or for additional processing steps and cost, you can place a buried oxide under all the FinFETs as shown on the right here to provide complete dielectric isolation. So this drawing shows how bulk NMOS and PMOS FinFETs and planar devices are both isolated using N and P wells. And I've tried to make the color coding of these two drawings very similar. Up on the top here, we have our bulk planar CMOS devices. And you can see we have an NMOS device on the left and a PMOS device on the right. And the NMOS device is sitting in a P well, which is connected to the P substrate. And the PMOS device is sitting in an N well, which isolates it from the P substrate. In a similar manner down below, here we have a bulk FinFET drawing, and we have again an NMOS device on the left side. You can see it has multiple fins. Everything sits in a P well, and that P well needs to have a P well tie, which is using one of the fins to create the P well tie. And this is very similar to the P well tie on the bulk CMOS device up above here. In a similar manner, we look at the PMOS device. In the FinFET, it sits in an N well, and it uses one of the fins as a connection down to the end-well device to act as an end-well tie. And this is done in a very similar manner to the way it's done in bulk CMOS, planar CMOS, where you have an N plus contact to an end-well to create an end-well tie. Now I'd like to go over a series of simplified FinFET fabrication steps. We're skipping hundreds of steps here just to show you the very basics of how the FinFETs are fabricated. So what we're going to do is we're going to start with a silicon substrate, and we're going to apply a hard mask. And this hard mask is possibly nitride, or maybe it's silicon oxynitride. Now you put photoresist on it, and you define the photoresist in the pattern that you want. Next, you move over here and you go ahead and etch the hard mask away. And you etch the hard mask, and then you remove the photoresist, and you continue and etch the fins all down through the silicon substrate. So now you have the fins. Now you strip off the remaining hard mask, and you oxidize the surface, and you etch it back to just expose the tops of the fins. And lastly, now we go ahead and we deposit a high K gate dielectric over the fins themselves, and then a gate conductor over top of that. And you etch and pattern everything, and you end up with the structure that we've shown before. These basic process steps create the transistor structure seen on the right. And the goal is to be able to create hundreds of billions of these devices on a chip. However, in order to do that, we first have to overcome some of the limitations of modern photolithography equipment. Much of the current equipment uses an argon fluoride laser with 193 nanometer wavelength. However, we want to be able to print geometries much smaller than that. Maybe 10 nanometers, maybe even smaller than 10 nanometers. So what tricks can be done to accomplish this? Well, the first trick is immersion lithography, where the printing is done through some type of liquid that has a much higher refractive index than just air. And the second trick is to use a laser with a very large aperture, which of course has some physical limitations. These manage to reduce the critical dimensions, or CDs, down to something in the maybe 80 nanometer range. However, we want even smaller than that. So the last two tricks I'm going to talk about today are double patterning and self-aligned patterning. By the way, in the picture down here, you can see this is a 22 nanometer tri-gate device, and you can see the fins run in one direction and all the gates run in the perpendicular direction. So let's talk about double patterning. It's also known as litho-etch. And this just shows a series of steps here. What we're going to start off with is we're going to start off with a silicon substrate with silicon oxynitride hard mask. We're going to apply some photoresist. We're going to bring mask number 1 here, and we're going to expose the photoresist in one area. Then we move over to the second part of this slide, and we bring in mask number 2, and it also has the same minimum pitch as our first mask, but it's slightly offset, and we expose more of the photoresist using mask number 2. Now for the third step, we come in here and we etch our developed photoresist, and it leaves a pattern behind. And now we use that pattern to etch the hard mask, and then we use the hard mask as a mask to go ahead and do our anisotropic etch for the fins. And what this does is it gives you 1/2 the minimum pitch. Now it required using 2 masks, one at a minimum pitch and a second one at minimum pitch, but then just offsetting the process slightly to expose something that gives you 1/2 the minimum pitch. Now, You might be able to do this with 3 masks or maybe 4 masks, but you can see that alignment between these mask layers are going to become very difficult after a while. You'd like everything to be perfectly aligned, but that never really happens. There's always going to be slight mismatches. So this works maybe for 1 or 2 iterations, but something better than this is needed. And by the way, this is why it's called litho etch, because you did a lithography step and then a second lithography step, and then you did your etch step. So this next technique is called self-aligned patterning, or litho etch. And the way it works is, now you have a silicon substrate, but we've stacked up a couple of layers, maybe a couple of hard masks with an oxide in between. And now we go ahead and we bring in our photoresist with minimum pitch. We define the photoresist, we etch the photoresist, and we use that pattern to etch down into the first hard mask, and it creates this structure to the right over here. And we're going to call these structures that were left mandrels. Now what we do is we come in and we deposit a spacer material that goes over and around the mandrels. And this is very similar to the spacer materials used to create spacers on standard planar MOS devices to the left and right of the gates. Now we have this spacer material deposited, and now we do an etch. And the etch is coming down, and it etches away this stuff equally, but because it's thicker around the sides of the mandrels, it leaves the spacer around the sides of the mandrels, but clears it out on top and on the sides of the mandrels. Now this is the same diagram we had before, so we're starting at this diagram. Now we come in and we actually strip the mandrel, so all it does is it leaves the spacers behind in this 5th step here. Now we use the spacers as a mask to etch the oxide, number 6 here, and we remove the spacers. So now we have the oxide defined, and it's at half pitch, and it's all been self-aligned. But we don't have to stop there. Now we come in with another set of spacers, and we deposit spacers around the oxide. We're using the oxide as a new set of mandrels. So once again, we deposit a spacer around the oxide. Now we move to the next. So this is the same diagram. And we come over here, we etch the spacer again, and it just leaves spacer to the left and right of the oxide mandrels. Now we strip out the oxide, and it just leaves the spacer behind. We use the spacer to etch the hard mask below, and then we remove the spacer, and the hard mask is used for our anisotropic etch, where we etch the fins. And this actually gives you 1/4 minimum pitch. So this gives you something called self-aligned quadruple patterning. And all these fins are completely self-aligned with each other. This is a technique that's used very commonly, and it allows you to make pitches that are smaller than your minimum pitch and still have the structure self-aligned. Now I wanted to go through some animation to kind of show you how this works. So we're going to do patterning and etching of the photoresist first. And once again, we start out with minimum pitch. The next step is to etch the hard mask. Now we remove the photoresist. Now we deposit the spacer material. Now we etch the spacer material, just leaving it around the mandrels. Next, we strip out the mandrels themselves. Now we etch the oxide below the spacer material. We strip out the spacer material. We deposit new spacer material around the new oxide mandrels. We etch the spacer material. We strip away the oxide mandrels. We etch the hard mask. We remove the spacer material. Now we etch the silicon using the hard mask. Now we strip the hard mask. And what we end up with is 1/4 minimum pitch, and it's all self-aligned.
So similar tricks are used for patterning the gates that lie perpendicular to the fins. So basically the whole die is covered by fins in one direction and gates in the other direction. And then something called cut masks are used to chop out sections of the fins and the gates to create individual transistors or transistor groups. So you start out with this whole big sea of fins and then selectively remove material with the cut masks as needed. And the gates are done in a similar fashion just later in the process. And if you look at this picture here, we have fins running left-right and gates running north-south. And then at some point you come in with cut masks and selectively remove the fins and the gates to create individual transistors. And if we looked at this picture over here, here is an individual transistor, and cut masks have been used to remove the fins and the gates around it, separating it from the adjacent gates and fins. The use of high K dielectrics and low resistance metal gate material was initially developed for advanced planar transistors. A slightly modified version of this technology is used with FinFETs. Traditional MOS transistors use silicon dioxide, that's SiO2, as their gate dielectric. However, the dielectric constant of silicon dioxide is 3.9 compared to the high K materials such as hafnium dioxide with a dielectric constant of 25. These high K materials can allow you to use a thicker gate oxide and still maintain the same transconductance, aka performance, of the transistor. A thicker oxide means less gate leakage and improved gate oxide integrity, which can lead to improved reliability. High K dielectrics can also enhance gate control and allow the transistor to operate at lower voltages, reducing power consumption. And if we look at this drawing over here, the high K dielectric is drawn in yellow, and it would be surrounding the channel on all three sides. Threshold voltages. Conventional MOS transistors use VTH adjust implants to set the threshold voltage by altering the channel doping. However, for performance and leakage reasons, FinFETs use fully depleted channels, meaning there's no doping in the channel area. The threshold voltages of FinFETs are adjusted using a different technique called a work function difference. In solid-state physics, the work function is the minimum energy needed to remove an electron from a solid up to a vacuum. Another way to say this is the work function is the energy difference between the Fermi level and a vacuum. The work function difference between the gate material and the semiconductor channel dictates how much gate voltage is needed to induce a channel and turn on the transistor. By altering the material used to form the gate, you can adjust the threshold voltage. And let's take a look at this energy band diagram over here. So this represents MOS, metal, oxide, and silicon. So the metal has a work function that's basically the difference between the Fermi level and the energy level of a vacuum. The silicon also has a work function, which again is the difference between the Fermi level of the silicon and the vacuum. The difference of these two work functions will dictate the threshold voltage of the device. What they do in FinFETs is they adjust the material used for the metal here to move this Fermi level up and down to adjust the work function difference to get the threshold voltage that you want. This is as opposed to placing more or less dopant in the channel as a conventional MOS device does to adjust the Fermi level of the silicon.
Now I'd like to discuss the gate last process, or the replacement metal gate process. The gate last process in FinFETs is a sequence of steps where a temporary dummy polysilicon gate is initially formed and used to define the fin structure and the source drain regions, after which this dummy gate is removed and the final functional high-K dielectric and metal gate stack is deposited. This is opposed to traditional MOS transistors where the gate is formed first before the source and drain regions. And if we went ahead and looked at this traditional planar MOS device over here, its gate is put down before the source and drain diffusions, and it's actually used as a mask to define the source and drain regions in a self-aligned manner. However, in the gate replacement or metal gate replacement process, this area of gate is actually initially polysilicon and then later gets removed and replaced with metal, and I'm going to talk about that in more detail on the next several slides. Here's a very simplified list of the gate last process steps. First, we fully etch the depleted fins from the silicon substrate to provide the backbone for the source, drain, and channel. And I think we've talked about this in great detail already. The next step is we oxidize the substrate, and that's this gray region here. And this helps to prevent the leakage to the substrate and between adjacent fins while reducing capacitance for faster switching. And I think we've probably mentioned that before also. The third step here is we deposit and pattern a dummy polysilicon gate, and that's what we show in green here. Now the poly is used for the dummy gate because it needs to be able to withstand the upcoming high temperature steps. And eventually this poly will be replaced by a stack of high-K dielectric and metal. The metal we're replacing the polysilicon with would not withstand the high temperature steps. Step number 4 is to implant the source and drain regions, and we use high doping for good ohmic contact, and that's followed by high temperature anneal. Now it's hard to see the source and drain regions here. This particular drawing, they're underneath the stressor material, but you can kind of see the implant off to the side here. Again, the fin is running left to right here. It's running underneath the stressor and the poly gate. So we'd be implanting the source drain regions on the left of the gate and on the right of the gate. Step number 5 is we deposit the epi stressors. That's these purple regions here. And again, we're typically talking about silicon germanium for the PMOS or silicon carbide for the NMOS. And I think we've talked about that previously also in some detail. Step number 6 is to create spacers around the dummy poly gate, and that's these two green regions here. And these are created in a similar manner to the spacers placed around traditional MOS transistors to create the lightly doped drain LDD structures. And the 7th step here is we actually strip out the dummy poly gate, which is this blue region in the middle here. And that's getting ready to replace this dummy poly gate with metal. Step number 8 is to deposit the high-K gate dielectric. And we're typically talking about something like hafnium dioxide with a pretty high K number. Step number 9 is we deposit a barrier metal, and this is typically tantalum nitride. And that's shown in the blue region here. And this prevents the copper from diffusing out of the gate region into the surrounding oxide. The copper really wants to move, and the tantalum nitride confines it to this space. Step number 10 is we deposit the work function metal. And
That's shown in red here. And different metal compounds are used for the NMOS versus the PMOS to set the desired thresholds. Typically, it's going to be some combination of titanium nitride or maybe titanium aluminum nitride. And the last step here is we fill the remaining gap with copper for low resistance. FinFETs are combined to create standard cell logic blocks, just like what's done with traditional planar transistors. However, there are a few differences. Due to the addition of the stressors, the PMOS and NMOS devices in FinFET blocks are typically the same size as each other, not the traditional 3-to-1 ratio that we're used to. The height of the FinFET standard cell is set by the number of fins. The height of the inverter cell shown here is set by 6 fins, 3 for the NMOS device and 3 for the PMOS device. Now, due to the way the fins are generated, all the transistors must run in the same direction, with the fins in one direction and the gates running in the other direction. Contacts, vias, and metal. FinFETs source, gate, and drain regions are so close to each other, it's difficult to contact one without shorting to the other. FinFETs use a self-aligned contact technique to make that possible. This technique was originally developed for nanoscale planar transistors. It works by recessing the gate and then capping it with some type of etch stop. Now, when you've etched your source drain contacts, if they're misaligned, the contact metal doesn't short to the cap gate. Contacting the gate can then be done off to the side. And again, let's take a look at this diagram down here, and we can see how this works. This is done for a planar device, but it would be similar for the FinFET. We come in here, we define our gate. We recess the gate, and we put an etch stop on top. Now when we come in to drive, to create the contacts, the source drain contacts, if they're misaligned, this contact will not make contact to the gate because there's a material in the way here. And you can contact the gate off to the side. So in this case, our gate contact would be maybe off to the side over in this area here, and allow for the source and drain contacts to be close to the gate but not making direct contact to the gate. Now, putting the gate contact off to the side, it works pretty well. However, it takes up more area, so it's desirable to put the gate contact directly on top of the device. However, this requires capping the source and drain contacts as well as the gate, and then selectively etching the desired material to allow contacting one without contacting the other. This adds complexity and creates the need for several special via and metal layers to provide connection from the various device terminals up to a traditional metal one layer. So if we look down here, this shows the gate contact off to the side. And this was pretty convenient. However, again, like we said above, it takes up area. So you'd really like to put that contact right smack on top of the gate region. But in order to do that, you have to do this special capping process. So not only are we capping the gates now, we're going to be capping the source drain regions and then selectively etching through these caps to allow self-aligned contacts and vias without shorting out to the adjacent gate or drain source contacts. So let's take a look at the metal stack. The metal diffusion MD layer and the via diffusion VD layer are used to connect the fins to a local interconnect layer called metal 0. You can see the fins are down here in the bottom, and we have the MD and VD layers here connecting the fins up to a metal 0 layer. These extra via and metal layers are the result of this complicated self-aligned capped contact process.
Now, in a similar manner, there's a via gate, VG layer, that also connects the gates up to a metal zero layer. So the via zero layer is used to bring the metal zero layer up to the traditional metal 1 layers. So the MD, M0, and M1 are all unidirectional interconnect layers, meaning they run in one direction only, no jogs. And typically all the metal layers are made of copper with a tantalum nitride barrier. Now, as the geometries have grown smaller, the barrier metal is taking up more and more of the area or the volume of the conductor. So they're looking at other metals that might not need a barrier metal or that might be more conductive at low pitches. And cobalt and ruthenium are being explored as alternatives to the copper metal with a tantalum nitride barrier. I wanted to give you a look at what the latest Intel processes are going to be using. And this is called backside power distribution, or I think Intel is calling it the power via. So when I was researching metal interconnect, I came across this novel approach that Intel is using on their future chips, and I thought I'd share it. Intel intends to embed their power interconnect in the underside portion of the wafer and then connect it to the front side using through silicon vias, TSVs. This means the transistor level would be sandwiched between metal above and metal below. And this is being done to reduce the resistance of the power interconnect and free up wiring channels in the topside interconnect. So let's take a look at the traditional interconnect. Normally you'd have your handle wafer down below, your transistor level here, and then all your interconnect layers, maybe 20 layers of metal, bringing everything up to the surface of the wafer. What Intel is looking at doing is taking all their power interconnect and putting it below the transistor layer. So the transistor layer in this case would be represented in the area that I'm highlighting here. All the power would come out on the bottom side, and all the signal and interconnect would come out the top side as it normally does. And again, this gives you additional channels to route on in the top interconnect, and it reduces the resistance for the power interconnect. So let's talk about what's next. 22 nanometer FinFET production was introduced by Intel in 2011. Since then, FinFET fabrication has propagated to all the major foundries and has basically taken over the majority of high-performance applications. Over the years, processing advances has squeezed more and more performance out of FinFETs by decreasing the fin pitch while increasing the fin height. And currently, TSMC has a 3 nanometer node in production, which is extremely impressive. However, it appears FinFETs may be reaching the end of their run, so we're going to talk about what's next here. Let's take a look at this diagram down below. So here's the 22 nanometer FinFET, and it was maybe 34 nanometers high. Then they moved to a 14 nanometer node, and the FinFET height increased, and at the 10 nanometer node, the FinFET height increased even more, and that was to keep the performance improvements moving as you shrunk the FinFETs down in one direction or dimension, they increased in the other dimension. So the next transistor geometry the industry will be moving to is called gate-all-around, or GAA for short. This geometry completely surrounds the channel on all 4 sides with gate material, improving the gate control. In addition, the GAA geometry allows vertical stacking of the conducting channels, and these are sometimes called nanowires. Conduction through each nanowire can be tightly controlled, and multiple wires operating in parallel can provide superior drive capability. And here's just some diagrams showing the propagation from a planar device to a FinFET device where the gate is on 3 sides to the gate all-around device where now we have gate completely surrounding these nanowires, giving improved control of the channel. And again, we can stack these nanowires in the vertical direction. So gate all around is only the 3rd time a major transistor geometry change has occurred in the almost 70-year history of the integrated circuit industry. However, gate all around is not some distant futuristic technology. It's here and now. Samsung already has an early gate all around node in production, and the other foundries are quickly following suit. I believe it's likely gate all around will become the dominant technology in the industry within this next decade. And here's just a SEM photo of a cross-section of some gate all around transistors, and you can see the stacked nanowires right here. So the death of Moore's law has been prematurely predicted many times. However, with FinFETs and gate all around transistors, Moore's law will probably be alive and kicking for many more years to come. It's an exciting time to be in this industry. So at the beginning of this presentation, I discussed the early history of the IC industry and gave you a little background on some of the visionaries that helped make it happen. Then I moved on to show how the advent of the FinFET has revolutionized the business, and lastly, I gave you a peek at the future with the gate all-around transistor. I hope you found this presentation both helpful and enjoyable. Thank you very much for the opportunity to speak today.